Compute the number of positive integers n between 2017 and 2017 squared, such that n to the power of n is equivalent to 1 modulo 2017. And we are given that 2017 is prime. And what modulo means is that it leaves a remainder of 1 when divided by 2017. So how can we get started on this problem? This problem may seem super simple, but finding out when this holds seems like a nightmare. Like, if it's hard to find out when a to the power of x for any a is equivalent to 1 modulo 2017, I'll just let p equals 2017 for now because it doesn't seem like there's anything special about the number 2017. So it seems difficult itself to find out when this happens. So in order to find out when this happens, we're going to define a new term. We denote the order of, with respect to p of a, to be the smallest integer x, smallest positive x, such that a to the power of x leaves a remainder of 1 when divided by p. And so we can end up doing a lot with this. For example, suppose that a to the power of b was equivalent to 1 modulo p. Then we can express b equals cx plus d, where c is an integer and 0 is less than or equal to d, which is less than x minus 1. So if we plug in that for b, we get a to the cx plus d is equivalent to 1 modulo p. And since a to the power of cx is equivalent to 1, since a to the power of x is equivalent to 1, that means that a to the power of d is equivalent to 1 modulo p. But if d is less than x and is not equal to 0, then that means that d is instead the order, but x is the order itself because it's the smallest possible one, which means that d equals 0. So hence we've derived, using this order notation, that if a to the power of b is equivalent to 1 modulo p, then this means that the order of p with respect to a divides b. That's the only way this can happen. And in particular, by Fermat's little theorem, we know that a to the power of p minus 1 is equivalent to 1 modulo p. So as a result, we know that the order of p of a divides p minus 1. And one final thing is needed in order to tackle this problem, and it is the notion of a primitive root. So a primitive root is a number g such that the order of, with respect to p of g, is equal to p minus 1. In other words, the smallest integer such that g to the x is equivalent to 1 modulo p is p minus 1. And this is guaranteed. G to the power of p minus 1 is equivalent to 1 modulo p always by Fermat's little theorem, unless g is a multiple of p. But when the order of g is equal to p minus 1, then g is called a primitive root. And it turns out that a primitive root always exists. There always exists a primitive root g. And moreover, the sequence of numbers 1, g, g squared, g cubed, all the way to g to the power of p minus 2 is just, when taken modulo p, this is just the list 1, 2, 3, all the way to p minus 1 in some order. And the reason why this happens is because if they weren't the same, then 2 of these numbers in the list must be the same. So g to the power of k is equivalent to g to the power of l modulo p. And as a result, this means that g to the power of k minus L, and we're going to assume that k is greater than L, is equivalent to 1 mod p. But this means that the order of g with respect to p must divide k minus L. So k minus L, p minus 1 must divide it. But this is impossible because k and L are always among these integers. So that results in k equals L. And hence g actually generates the whole list. And for this very reason, primitive roots are also called generators. And the next special thing we can say about primitive roots is that the order of g to the x with respect to p is just equal to p minus 1 over the GCD of p minus 1 and x. And that's the key theorem. So how do we go about proving this? So to prove this, we just know that that the numbers are g squared, g cubed, all the way to g8 to the p minus 1. And this equals 1. And g to the power of x is somewhere in this list. And if we apply it to pose y times, then we want to find out the smallest value of y such that this gets all the way back to p minus 1. So we've reduced it to finding out the smallest y such that xy is equivalent to 0 modulo p minus 1. In other words, y takes the rest of the prime factors of p minus 1 that x didn't cover. So given this prime factor notion, we might want to let x equals z times GCD of x and p minus 1. And in this case, that means that z is relatively prime to p minus 1. So GCD of z and p minus 1 is equal to 1. So plugging in, we get zy times GCD of x and p minus 1 is equivalent to 0 mod p minus 1. And dividing both sides by z, we can do that since it's relatively prime. We get GCD of x and p minus 1 times y is equivalent to 0 mod p minus 1. So now what? Well, we now know that this has all prime factors of p minus 1. So the best we can do from here is just set y is equal to p minus 1 over this GCD. Because that's the smallest number that will cover the rest of the prime factors. And this will work because it's GCD times p minus 1 over the GCD, and the GCDs cancel out. All right, so now we've proven that the order of g to the power of x with respect to p is equal to p minus 1 over GCD to the p minus 1 and x. With that, we can now solve the problem. So now we're back to the problem, and you can go ahead and pause the video again if you want to reread it. So given this notation of orders, we might note that the period of the exponent by Fermat's little theorem is 2016, and the period of the base is 2017. So if we increase n by 2017 times 2016, then this thing ends up being unchanged. And surely enough, this length here is of length 2017 times 2016 plus 1. So if we can get rid of that plus 1, that would be really good for us. But we can easily do that since we can subtract 1 from that. And we can do that because 2017 squared obviously does not work. So now we reduce it to the number of residue classes modulo 2016 times 2017, such that n to the power of n is equivalent to 1 modulo 2017. And equivalently, by the Chinese remainder theorem, the Chinese remainder theorem, for those of you who don't know, states that for any residue class modulo 16 and any other residue class modulo 2017, there exists a unique residue class modulo 2016 times 2017, which is equivalent to both. And by this Chinese remainder theorem, we want to find out the number of ordered pairs A, B, such that 0 is less than or equal to A is less than or equal to 2016. 0 is less than or equal to B is less than or equal to 2015. And A to the power of B is equivalent to 1 modulo 2017. So obviously A equals 0 doesn't work, so we can get rid of this and turn it into a 1 is less than or equal to A is less than or equal to 2016. But now, luckily for us, we know that there's a primitive root, suppose G. Then all the possible values of A, modulo 2017, are just G, G squared, G cubed, all the way to G to the power of 2016. So now let's find out what values of B work for these. Suppose we have G to the X. Then G to the X to the power of B is equivalent to 1 modulo 2017. But this means that, but from what we discussed earlier, this means that the order of this must divide B, but the order is just P minus 1, which is 2016 in this case, divided by the GCD of X and 2016. It divides B, and that's necessary and sufficient. So we want to find out the number of integers in this list that end up being divisors of 2016. Ends up being multiples of this number here. And for obvious reasons, since this is a divisor of 2016, this is 2016 over 2016 over GCD of X in 2016. So this is GCD of X in 2016. And if we sum this for all X, we've reduced to the problem to finding out the sum GCD of 1 in 2016 plus GCD of 2 in 2016, and etc., so on and so forth, plus GCD of 2016 and 2016. So we've gotten rid of all the stuff from the problem statement, but even this seems almost as worse to compute. So how can we go about computing this sum? So let's go ahead and let this be f of 2016. And we want to try finding out a simpler form for the function f. And before I do this, I will define Euler's Toshin function, for those of you who don't know, to be the number of integers between 1 and n inclusive, such that the GCD of x and n is equal to 1. This will end up reducing the note, making things a lot easier to write. So for each GCD, we know that each GCD is a divisor of 2016. So let D be a divisor of 2016. We want to find out how many of these GCDs are equal to D. So GCD of X and 2016 is equal to D. But this means that the GCD of X and 2016 over D is equal to 1. So by Euler's Toshin formula, by the Euler totient, there are phi of 2016 over D possible value. That's how many integers between 1 and 2016 that satisfy this here. So we reduced it to finding out the sum D times phi of 2016 over D, where D divides 2016, obviously. But this seems almost as scary, if not worse, because we've introduced a new function here. Well, luckily for us, it's not that bad. If we let this be f of 2016, then that means that we want to try dividing both sides by 2016. So that's because that will make things a bit nicer. Over 2016 is equal to the sum when d divides 2016 of phi of 2016 over d over 2016 over d. But because 2016 over d is also a divisor, this means that it's also equal to d divides 2016 of phi of d over d. So how can we continue from here? To find out this sum, we will first have to, I'll first claim that phi of AB is equal to phi of A times phi of B. I won't prove this here because the proof is kind of complicated. So, but the point is that this ends up being like, if this equals f of 20, so actually this should be g of 2016, then we prove that g of 2016 is equal to g of 7 times g of 9 times g of 64. And 64, this should be 32. And 32 times 7 times 9 is equal to 2016. That's a useful fact you should know. In other words, we want to prove that g of xy is equal to g of x times g of y, where x and y are relatively prime. So this ends up being the sum of, from where d divides x, of phi of d over d times the sum of the divisors where e divides y of phi of e over e. Then if we combine these two, we end up getting the sum of d divides x, the sum of e divides y, of phi of dE over dE. And we can end up showing that dE divides xy, obviously, and that's actually necessary for this to happen. And we can split it, and since x and y are relatively prime, we can undo this by finding the factor that divides x and the one that divides y. So this ends up being xy. So now that we've proved that this function is multiplicative, because 2016 is equal to 7 times 9 times 32, as a result, we know that f of 2016 is equal to f of 32 times f of 9 times f of 7. In other words, the function f is called multiplicative. This argument might seem really long to prove it's a very simple thing, but once you know the whole gist of the argument, you'll always be able to use it. So now all of these terms here are pretty straightforward to compute. So f of 32 is equal to GCD of 132 and all the way to GCD of 32 and 32. And so there are 16 terms that are divisible that make it 1. There are 8 terms that end up making the GCD 2. There are 4 terms that make the GCD 4, 2 terms that make the GCD 8, 1 term that makes the GCD 16, and another term which makes the GCD 32. So the sum ends up being 16 plus 16 plus 16 plus 16 plus 16 plus 32, which is 112. So that's f of 32. Now f of 9, that is equal to GCD of 1 and 9, and then plus other terms. So there are 6 terms that result in GCD 1, the ones that are not multiples of 3, 2 terms that make it 3, and then 1 term that makes it 9. And evaluating the sum, it's 6 plus 6 plus 9, which is 21. And f of 7 is just equal to 6 times 1. There are 6 terms that give GCD 1, plus 1 times 7, which end up being 13. So therefore, our answer is 112 times 21 times 13, which is 3,576 after a bit of computation. So this is a very complicated problem, but instructive in the way that it introduces orders modulo of prime. And we reduce it to this. And using that, we could use a Chinese remainder theorem to reduce it to this. Using primitive roots, we reduced it to finding out this sum here, which ended up being a bit more complicated than we thought. But after proving that this function is multiplicative, we were able to finish off the computation quite easily. So thank you so much for watching this video. I hope you enjoyed. Please get me to 125 subscribers before the AMC 10A on November 8th.